Okay, so today I will use the blackboard in order not to go too fast. And the first half of today's lecture will be about the emission of gravitational waves and the method which has been used to compute to high order the emission of gravitational wave by binary systems. Although in the rest of what I will discuss, which is the Hamiltonian and the transcription between the Hamiltonian and quantum scattering amplitudes, I will not really need the gravitational wave emission. This is something which is also of interest in quantum field theory. For instance, there is recent work by Strominger and especially Sen on soft graviton emission, which is connected with some of the structures of this that I'm going to talk about. Anyway, I want to discuss the method which has been used to compute the emission of gravitational wave from a binary system. And I will, so this method is called multipolar post-Minkowskian scheme, and or MPM in short. And I will start explaining the very elementary thing, which is how to deal with multipolar expansions in linearized gravity and how to compute the gravitational wave emission of an arbitrary source. And for this, let me explain quickly what means really multipolar, because sometimes in the literature, multipolar means expansion in YLMs, in spherical harmonics, and then actually it introduces a lot of confusion because there are two things which are confused in the YLMs, and this is what I want to explain. Multipolar means an expansion in irreps, irreducible representations of SO3. So what it means is that you are solving PDEs which are invariant under the group of rotation. Okay, and then you decompose the solution, you express the solution, especially at the linearized level of these PDEs, in irreducible representation of the rotation group. So it looks obscure this way, but let me say really what it means. First, yes, we are going to discuss a solution of field equation that looks something like that. I have a function. Actually, for gravity, we will have 10 functions of space and time, which satisfy type of wave equations, although they are more complicated than that. And when you look at this equation, where this is the D'Alembert operator in flat space-time, this operator is invariant under rotations. What does it mean? It means that if I have a solution of this equation, I can get a new solution phi prime of t of x, which is different and which is obtained from the first solution by applying a linear operator depending on 3 Euler angles, which rotates the solution. And the way it rotates the solution is by not touching time, but changing space by actually the inverse rotation of this. Because if you want the rotation, if you want the group law to be satisfied, I say if you compose two operation rotation, you have to act on the argument with the inverse. Okay. So physically, what it means, and this is what you will have to keep in mind, is that we are going, so in order to do that, we will have a function that depends on t. X, I decompose x, the vector x, as being the radius, that is to say the distance between some origin and the point in space where I am, times a unit vector. So what will be important in the following is that here I have a function which is a function of time, r, and then a unit vector, because this is the unit vector which rotates under rotations. And what means an active, so these rotations will be active, which means that when I have an original solution, let us say, which on the sphere is stronger, let's say, it is something which varies on the sphere, and it has a big bump here, the rotated solution will be a solution where this bump is rotated by the rotation r. So this is a different solution where you rotate the thing, just because sometimes it's confusing. It's not just a coordinate change or whatever. I want really to think about this rotation. And when you think about rotations in this active way, in order to rotate the solution this way, what it means is you have rotated the source, okay? Because behind this solution, there will be a source in the middle, and what you really do is the source, you know, is something, and you rotate it, okay, in space. Now, we want to decompose. Now, let's look at this function as function of the angle. So, n means a unit vector. N is a unit vector on the two-sphere, okay? Which means, so in its Euclidean square is equal to 1, which means it is parametrized by two angles, theta phi on the sphere, like cosine theta, sine theta, cosine phi, etc. Okay, but we want to write things without using coordinates theta phi. We want to keep things with Cartesian coordinates as far as possible, which means that I want to consider a function. Let me write here. What is, so now let me consider at fixed time and radius a function on angles on the sphere. What means to decompose this function in irreducible representation of the rotation group? Let me just give the answer. The answer and the representation we will use is that we will decompose it in an infinite series going with an integer going from L equals 0 to infinity. So for each L, this will be the multipolar decomposition of this function, and each L as a function of n will be written in the following way. Okay, actually it's not needed. Yes, what it means is this object is a Cartesian tensor which is symmetric and trace-free with L indices, which is symmetric and trace-free over all indices. This means that it is a tensor with L indices. If I change indices, it is symmetric. If I try to take a trace of any two indices, I get 0. Let me give you an example. For instance, if I start with an example of a tensor of this type, would be I can take any tensor Tij. Then I can take its symmetric part. So Tij with parentheses is 1/2 of Tij plus Tji. And then after taking its symmetric part, I can take this minus 1/3 of the trace with respect to these indices delta ij. And now this object is a tensor that I will denote T hat ij or Tij with the brackets around here, defined this way. As you can see immediately, it is a symmetric tensor. If I take a trace, I get 0. Okay. So for each order of the tensor, you can project tensors on the set of STF tensor with L indices. And now an easy calculation is if you count the dimension, how many tensors exist which are, yes, Vasilisa?
Sorry, could you tell me again what does F mean?
So F here is it's the notation for a general tensor. What I'm writing here is that it's a decomposition. Usually when you have a function of theta phi on the sphere, if you take a textbook, they say, okay, let's decompose it in YLMs, okay? Which would mean you would decompose the function of theta phi in something like FLM spherical harmonics, you know, YLM of theta phi. Okay? What I'm saying is that this is not very convenient and it hides the structure of the thing. I am looking at this is a double sum over m going from minus L to plus L and sum over L from 0 to infinity. I'm saying the sum over m over the magnetic number of this thing is equivalent to what I'm writing. It is actually, okay, there are two L plus 1, that was what I was going to say. Here there are two L plus 1 independent components of YLMs at order L. But now if you count the number of symmetric trace-free tensor, the dimension of the space of symmetric trace-free Cartesian tensor of order L, you find that it is 2L plus 1. Now evidently this is a representation of the rotation group in the sense that if I take a tensor which is symmetric trace-free and I rotate it now means if I do an active rotation, with indices ij acting on each thing, I take a tensor with L indices. On each index, I rotate it to define f prime I1 equal this, and then I2, I do this with... I take a tensor with L indices. I rotate each index by the same rotation matrix. It's clear that if it is symmetric trace-free, after rotation, it is also symmetric trace-free. So it is a set of Cartesian tensor which has the correct dimension, 2L plus 1, and which is invariant as a set under rotation. It's a representation. It rotates as a set. And this is actually a very good way of representing inside the YLMs. YLMs, as we will discuss very briefly, is just a particular basis which selects special, it's a basis in this space. While if you say I take a generic tensor in this space, you don't need to say on which basis it is represented. It's like using, a vector. You don't say it's 3 components. You say it's a vector, and it is a representation of the rotation group.
Just an expansion as a polynomial in the component of the vector n.
Yes. So at the end, what it means is a generic function on the angle can be decomposed, except that this is a series. So each one is a polynomial.
Yes.
Polynomial in L, but I include the infinite number of polynomials. So at the end, it is an arbitrary function. And for any C2 function, twice differentiable function, this thing converges in the L2 sense and things like that.
Okay. It could be in SO3, or this works also for generic for higher sphere, right?
Yes, sure, sure. Except that except that now when you are in higher dimension, you have more Young tableaus. Okay, in 3 dimensions, the only Young tableau you have is you can have more representations. Like for instance, when we use DIMREG and had to extend gravitational wave generation in higher dimension, we had to use new tableaus, also Young tableaus. I'm in 3 dimensions here for this.
Sorry, how does this depend on n? It's not clear. What did you write?
Sorry. So what I wrote is the tensor product. It's just the product. I don't even need this because it projects out. I take it's the product of n vectors. Okay. Let me give an example. For instance, the beginning of this thing, okay, is a constant without indices. Then the first term in the expansion will be fi ni, so a linear function of the unit vector. This is the dipole. It's the spherically symmetric. It's the L equals 0 part of the function on the angles. This is the vector part. It's the dipole part because it contains a special vector. If I had only this function, it would be positive on half of the sphere, negative on the other half, depending on the direction of f. Then the next term would be Fij symmetric trace-free Nij, which, if I write it explicitly, is equivalent to Fij, Nij, because this is symmetric trace-free, so I can take away the trace. It does not count the trace here. Then you see I'm proportional to a polynomial in Nij, which is now like a pear-shaped thing, quadrupolar thing. It's just the decomposition of a function on the sphere, but it's very convenient to write it in terms of polynomials of arbitrary order, and the coefficient of these polynomials are tensor which are symmetric trace-free. Now, why is it useful for solving any equation? Is that if now let us say I want to to start, yeah, I should speed up, sorry, equals 0. Quickly, if I am solving, I want to write why it is useful to write the general solution of Laplace equals 0, okay? Now, let me state that if I choose an origin, the general solution of this solution will depend in the domain in which I look for a regular solution. If I look for a regular solution which includes the origin, and I want it to be regular at the origin, I can, okay, so what you do is you can write the general solution as a sum over L of a certain function phi L of R of what I wrote here. So you write the coefficient, yes. So now let me introduce a convenient notation. When you deal with tensors with L indices, you always have the problem is, are you going to write I1, I2, IL each time? So it is convenient to introduce a notation we introduced with Luc Blanchet, which is when you have a multiplet of small L indices, you represent it by just one thing, which is capital L. It's not the notation of mathematicians, by the way, but it is convenient where this L is the same as this L. So if I have n indices, I will represent it as capital N. Okay, so the information about the length of the thing is contained in the name of the thing. And then this thing you write as FL NL, where each time you have a multi-index, you just write L indices, and L to the power L is also the tensor product. It's just a notation, but it's once you are used to it, it's very convenient. Okay, so this thing would have this form, okay, where if this is symmetric trace-free, this is also symmetric trace-free. Now, if you replace this in the Laplace equation, you find, as we all know, that this solution has to be proportional to the Lth power of R if you want to solve the Laplace equation. So what you find is the generic solution is something like CL R to the L and L, okay, where this is symmetric trace-free, okay? So this is a way to represent the general regular solution, regular at the origin. If you want the solution which, instead of being regular at the origin, is outside a certain sphere and decays at infinity, actually it is, so this is at the origin, and the other one is at infinity, and the general solution will be the sum of the two in general. It will be of the form dl nl 1 over r l plus 1. These are the two types of solutions, which means what? Which means when I write this, this is d0 plus di ni over r square plus dij ni nj minus 1/3 of delta ij over r cubed, etc. to infinity. But this is a dipole solution of the Laplace equation. This is a quadrupole solution of Laplace. So it's just a way of writing the general solution. But now you see that these objects, these tensor, they parameterize. In this case, they parameterize the multiple moments of the field. Like this is the monopole part of the field outside an object. If I have an object in the center and I looked at the solution of Laplace of phi equals 0 outside, it will have this decomposition, and each tensor coefficient here represents a multiple moment of the field. And when you decompose the Laplace operator as 1 over r square dr r square dr plus 1 over r square, the Laplace operator on the sphere, and the reason why this formula works is that because you find also that the Laplace operator on the sphere, on the unit sphere, this delta index n means, you know, 1 over sine squared d by d. I mean, you open Messiah and Messiah, and then you find, when you need a formula, it's always very convenient. You find that the Laplace operator on the unit sphere, when applied to the function, which is the tensor product of L unit vector with all traces taken away, like this quantity for L equal 2, you find that it satisfies minus LL plus 1, the same function. Okay, so another way of saying what I'm saying is that this function on the sphere is an eigenfunction of the Laplace operator on the sphere with eigenvalue LL plus 1, which is part of the business that we all know. But now there is a very convenient way of rewriting this, which is here I have a function which is NL over R to the L plus 1. Why is this function in 1 over R to the L plus 1? Is there an easy way to understand this? The easy way is that this thing can be rewritten as, let me take this away, as sum over L of a coefficient which differs from this tensor just by some numerical coefficient that I don't give here. dl of 1 over R. What means this notation? This notation means I take the function 1 over R, I differentiate it L times, so this is a repeated, dl like NL is the tensor product of partial derivative in space, and 1 over R is a function of Laplace equals 0 outside the source. Therefore, if I differentiate 1 over R, it is still a function of Laplace equals 0. So what this is saying is that if I have the fundamental solution of Laplace equation, 1 over R, if I just differentiate over the Cartesian coordinates L times, I generate another solution. But if I take its symmetric trace-free part, I have transformed this solution in something which is also an irreducible representation of the rotation group, and a multiple expansion is just this. So once you understood this, so I never use YLMs here, you know, then the next step is, okay, how do I relate? So these are the multiples of a general solution of Laplace equation in vacuum, but they are not related to the source. This is a way to decompose the function in space in a dipole part, a quadrupole part, and things like that. I still need to say what is the expression of this thing in terms of the source of the mass distribution. And I will just give the answer. The answer is the following. The answer is, let me give the proof. Okay. If I want to solve Laplace of phi of x equal now something with a source, this was the decomposition when I was outside here and I did not know what was inside, okay? But if now I know I satisfy the Poisson equation with a certain source rho, I can use the Green function for, now I use the fact that Laplace of 1 is minus 4 pi of delta of x minus y, three-dimensional delta. And then this tells me that phi at point x is the integral over, it's the Poisson integral, rho of y, 1 over x minus y. Okay? And now what you can do, let's do it, is to x is the, I have the source here, the point y is inside the source, I am at the field point x, which is outside of the source, so this x is larger than y, so I can expand this in Taylor series in y. When you expand this in Taylor series in y, you have some integral of d3y rho of y. What is the Taylor theorem? In our notation, the Taylor theorem is just, you know, there is minus to dl, let me write it, yl dl 1 over x. Actually, the notation is such that Taylor theorem, you expand as if y was one variable. Taylor means, you know, f of x plus y is some. There is a minus sign, so there is minus to dl. There is 1 over factorial l. And this yl means, I remember, remind you, y1, y2, yil. And this means a repeated derivative, but you know, it's the same formula as if I had a function of one variable. So it's very convenient notation. And then once you have this, you realize that it has exactly this form, and you get that the multiple moments you get in frontier, the d prime L as tensor is just minus L over factorial L integral over d3 y rho of y yl. So with this yl, sorry, symmetric trace free here. Okay. So what you have done is decompose indeed now the source is decomposed in multiple moments. Okay. So modulo this factor that this is the usual Lth order multiple moment of the source. For instance, if L equal 1, this is the dipole moment, integral of rho vector. If y equal 2, you have yj minus 1/3 of y squared delta ij, the usual quadruple moment. Okay, this was just, okay, to introduce some notation for the Laplace equation. Now, what is the link with YLMs? By the way, this way of doing things was the way Maxwell was doing things, okay? Maxwell was, and how at the time, if you read Maxwell, he introduces the multiple moments, not in the YLM sense, but in the following way. He's saying that if I give myself directions on the unit sphere, a certain number of directions which correspond to certain vectors, like V1, V2, unit vectors, V3. If I take the function 1 over r, and which is a solution of Laplace equals 0, and if I differentiate it along the directions V1, V2, you know, directional derivatives, derivative along V1 times derivative along V2 times of the function 1 over r, I will have a general solution of Laplace equals 0. And this is what corresponds to multipole if I have, so each one of these things defines a pole. That's why they are called multipoles on the sphere. And if I take like 3 poles, I differentiate 3 times. This is the pole, third pole, okay, octupole. 2 to the 3 being 8. This is the way Laplace, Maxwell was doing things. And now what is the basis of YLMs, just for your information? The basis of YLMs consists on the sphere in taking special vectors, one along the z-axis, and you take it, let's call it E0, which is the vector along the z-axis. You differentiate L minus m times along the E0 direction, and you take another vector, which is, let's say, E plus 1, being defined as, okay, E plus 1 and minus 1 is defined as minus m plus Ex plus I Ey over square root of 2. Given a Cartesian 3-vector Ex, Ey, Ez, you define E0 as being Ez. So you can differentiate L times with respect to L0. You take one of these complex combination, and then if you differentiate L times with respect to E0, and L minus m time, and m times with respect to plus 1, so you do this. This is a YLM, okay? This is a way to see geometrically, because this obscure definition of YLMs is really obtained by this. Okay, just to... But I won't use the YLMs, because the YLMs is a special basis, is a way of choosing special things on the sphere. Why it is important not to choose a basis. Yeah. Now, this being said for Laplace equation, how do you generalize that for gravity?
No, okay. Sorry, the plus minus 1 should be in front of the I.
So yes, you're right that I put it. There is also, by the way, a minus plus in front, and also here. Yes, these are complex conjugate modulo sign. This strange sign convention is linked to spinor things. Okay, that's why there is a minus for plus. Okay, but that's not important. Definition of helicities. They are always troublesome. We want to generalize this to Einstein's linearized gravity. And by the way, we were surprised when we started working on this at the end of the 80s that nobody had done it correctly before. That in 1991, we were the first one to write a full multipolar expansion for linearized gravity and how to express the multiple moments outside the source as an integral over the source. That is to say, a generalization of the simple thing for the Laplace equation. You know, what is the problem? The problem is
it's not contained in Hermann Weyl.
No. Come on. I have respect for Hermann Weyl, but he did not care about such details. He left this to lower scientists, lower level scientists. Okay, to do that, we generalize in step. That is, we need to replace the Laplace equation by a D'Alembert equation with source. Okay, so I will now sketch things. So you have let's start with just a scalar. You have a function which satisfies, let's say, this equation. I have a source function of x and time, and I want to repeat this. Okay, so the basic idea is, what was the basic idea here? I was saying that if I have the source here, but if I look at the solution outside the sphere, so that I here in space and time here, outside, you know, so I don't see what is the source, I can immediately generalize this thing, because the only thing I used here was what was the fundamental solution of my operator. The fundamental solution of Laplace was 1 over r. The fundamental solution of the D'Alembert equation is a retarded wave, because I'm now going to impose the boundary condition, you know, that I'm looking for outgoing waves with the boundary condition that the field was 0 in the past. So I replace 1 over r by a function of t minus r over c. It's a solution of Laplace D'Alembert equals 0, which means immediately that the general solution I can write as sum over L greater than 0. Now, as in the classical calculation, there was this factor so that I could recover in the static limit the usual multiple moments, like the dipole being the integral of the density times the position, you know, without factor. You put this factor in front. Then you say, let me write the thing and just discuss. If I write this formula, this is a decomposition over all L. This L, let me remind you, means a multi-index, I1, I2, IL. So it's a repeated derivative of an object which is a Cartesian tensor with L indices, but considered as a function of the retarded time t minus r over c over r. This is a solution of D'Alembert equals 0. The fact that this is now L indices symmetric trace free means it is an irreducible representation of the rotation group. If I differentiate L times, all indices are contracted. I have a scalar, so I have a scalar solution decomposed in irreducible representation. So immediately, you know this is the generic multipolar decomposition of D'Alembert equals 0. But now, you need to express these objects in terms of the source, okay? And this actually is a slightly non-trivial calculation. If you open the textbooks, for instance, you could say this has been done for electromagnetism for years. Okay, so you say, let's open Jackson. But then what you find is Jackson says, let's decompose in omega, in Fourier, in time. And everything is done with Fourier. And in Fourier, you have Bessel functions and things like that. And you never write things in the time domain. If you want things in the time domain, actually, Fourier is not what you want. Okay? And even for electromagnetism, it had not been done in the time domain. Okay? And for scalar things also. Let me just write the final formula. The final formula that we derived with Luc Blanchet in 1989 is that this object, okay, which is now the multiple moment as a function of one variable, which is retarded time here, but I call it simply time here, is similarly to this, it is an integral over the source of something, but this something, where did I put, so yes, let me write this, SL T over X. Okay, you find that you can write this FL in the usual way as the integral over space of a repeated XL, so dipole, quadrupole, so it looks like something very ordinary, except that here I have an extra operation that this S bar of L, which is a function of t and x, itself is written as an integral between -1 and +1 of dz of delta L of z times the source, the original source, this one, t plus z x divided by c x. So the ordinary formula, if you are at the Laplace equation, is you integrate, you don't have this integration and you don't have this shift of time, okay? And delta L of z is not the delta function, but it is an approximation of the delta function. It is the following function. In the shade. Delta L of z is 2L plus 1 double factorial divided by 2L plus 1 factorial 1 minus z squared to the L theta of 1 minus z squared. This is a function of z between -1 and +1, which has this shape, and when L is large, it integrates to 1. Okay, so and then then it also, because it is 1 minus z squared, it is concentrated near z equals 0. So for L infinite, it is a delta function at z equals 0, but for L equal 1 or 2, it is spread out all over. So what this is saying is you can express the multiple moments outside in the ones that appear in the field as integral over the source, but this source is weighted by also integrals. There is an average going on over time shifts. Okay. Now we generalize this to linearized gravity. Okay. So once you have the general solution of this with a scalar, we are going to reduce gravity to the D'Alembert equation, and then at the end we will have formulas for the multiple moments expressed as integral over the source. Okay, I will now skip some details, but let me discuss linearized gravity. So linearized gravity, we start from Einstein's equations. By the way, the linearized gravity case was done by Bala, Ayer, and myself in 1991. If you want to see also with electromagnetism, I mean, we did the thing there. And so I remind you, Einstein equations are Ricci tensor minus 1/2 of R G mu nu equal 8 pi G T mu nu. And I do the linearized approximation of Einstein's equations. So for this, I need to take the Ricci tensor, which is contain two derivatives of the metric, and take its linearized approximation in the case where the metric G mu nu is written as Minkowski space plus H mu nu. That's the, let's say, usual notation. H mu nu is a small deviation from Minkowski space. I linearize Einstein equation first order in H. Okay? You find that R mu nu linearized is -1/2 of the Laplace operator acting on H mu nu plus d mu nu of H minus d mu sigma H sigma nu minus d mu sigma H like mu. Okay, so H means the trace. So H means the trace over eta mu nu of H mu nu. This is a repeated derivative, space-time derivative. The bar here is a notation of Einstein in the old days. It just means that you raise this index by eta mu nu. So you could put it up, but it's convenient to see it better down. But if you put it down, you are not allowed in principle to put nothing, because this would mean the sum over sigma without a matrix. Okay, why you need eta? But Einstein said, okay, let's just put a bar, and then it means it is contracted by eta. Now, this term and this term, they can be combined, and you can see that if I introduce h bar mu nu, which is h mu nu minus 1/2 of h eta mu nu, that d nu of h bar mu nu is this term with a plus sign minus 1/2 of this term. But then it means that the sum of these three terms is actually the combination of two terms involving this. So if I use a gauge, if I go to a coordinate gauge where this thing is 0, this term disappears, okay? This is the harmonic gauge in linearized approximation, which in the literature sometimes is called Dodonder gauge, many gauges. In mathematics, it's called wave gauge. It has changed many names. Actually, Einstein knew it already in 1912. You know, in 1912, Einstein used it. This was used in the mathematical literature for already in the 19th century. In this gauge, you find that the Ricci tensor becomes just this term, so it becomes the Laplace operator, and Einstein equation become Laplace of h bar mu nu, where h bar D'Alembert, sorry, yes. We are near the place, yes. Okay. So now Einstein's equation in this gauge, you see at the linearized approximation, it looks exactly like Maxwell equation, D'Alembert of A mu equal minus 4 pi J mu, except that the source J mu is replaced by T mu nu and H is H bar, and satisfy this. The conservation of T mu nu, d nu of T mu nu equals 0 is linked to this gauge. Okay, so it's exactly like Maxwell equations. So now what you can do is to say, okay, now I can write the general solution of Einstein's equation. What will I do? I will write it as a sum of repeated derivatives of this type. I want a retarded solution. I want a decomposition in multipoles, so I write symmetric trace-free tensors. And then I will write immediately Einstein's, the general solutions, okay? Yes, by the way, just, yeah, no, I will, actually, you need some technology to do that, because, for instance, you find this way that the general 0,0 component, where 0 means time, can be written as 4g over c squared, sum over L minus L over factorial L. Let me write this. Yeah. Okay, if U means denotes the retarded time t minus r over c, IL is a symmetric trace-free tensor with n indices. This is a solution of D'Alembert equals 0. So this is a solution of this thing outside the source. And then we will discuss, now let me state the theorem, okay? The theorem is, you find that you can write the generic solution of Einstein's equation outside the source, decomposed in multipoles, as a sum over multipoles, but there are two types of multipoles. When I had a scalar thing, I had only one type of multipole, the usual multipole, dipole of the source, quadrupole, etc. When you are in gravity, you find, by the analysis, that there are two types of multipoles. Multipoles which are like mass type. They are like integral of T00 plus corrections over the source, so they look like the Newtonian. But there are also spin multipoles, multipoles linked to the fact that the source might be rotating, that there is angular momentum in the source, and you might think there could be more multipoles, but no. The proof is that modulo a gauge transformation, you just need to give two infinite sequences of multipoles of the mass type and spin types, and this represents the general solution. Like, for instance, let me write what is h bar 0i, and then you can write all components. Yes, here the indices I and j are in space. They go from 1 to 3, while 0 is the time. Okay. Yes?
Okay. So the fact that you are still in this gauge is ensured by the fact that, I mean, it's a question about the previous step. So at some point you basically said the fact that the T mu nu is this is actually what's ensuring that you stay in the dollar gauge. So how do you, I mean, if I start with the solution, I have h00 and so on. How do I know that I always have d mu of h mu nu zero.
How you go to this gauge if you are not in this gauge?
No, but if I am in the gauge, how do I know that? Because on there, I'm solving the scalar equation for all the
Yes,
for all the components.
you check that what you write as a solution will be in the gauge. Yes, you have to check this.
But it's ensured from the fact that d nu of t mu nu is 0?
Yes, it is ensured. That is, if you write the integral formula, because you can also write that h mu nu is the retarded integral of t mu nu over the source, so it's the solution, let's say not decomposed. And from this thing explicit, you find that it satisfies this because of the source. So you are guaranteed
so
before.
Consistent source gives that.
Yeah, there is consistency completely, okay, at the linearized level. And the point is, the consistency will exist at all nonlinear levels, but this is what I want to describe now. So let me write the second formula, where it's not c squared but c cubed. If you keep track of the powers of c, which is convenient for the Newtonian expansion, there is a sum. This sum starts at 0 here. There is a sum where L starts at 1, where this is minus 1 to the L factorial L, d L minus 1. I will explain what it means. I dot time derivative of I L minus 1 of u divided by R, minus 4g over c cube, sum. These factors here, like minus L, they are just for normalization convenience. They are not very important. Epsilon IAB conceptually, I mean. They are very important technically. J B L minus 1 of u over R. Okay, let me explain quickly what I wrote. Plus gauge. First, this notation, L minus 1, remember L is a multi-index. L minus 1 means a multi-index with one index less than before. Okay, so instead of I1 to IL, you stop at IL minus 1. But it's convenient this way, you keep the notation. So this is, here in this component, there is the time derivative of this object which enters, and there is a new multiple moment called J. You see, with also symmetric trace free with L indices. So these are the two sets of multiple moments, IL called mass multiple moments, JL, J like angular momentum, which are multiple moments linked to the angular momentum of the source. And then I will not write things, but then you have explicit formulas that say that IL and JL are some integral over the source, which are of this type, but more complicated because you need to do some algebra of transformation to irreducible tensor. Okay, so anyway, it's technology, okay? There is an explicit formula which writes the multiple moments seen from outside as integrals, but weighted integrals over the t mu nu of the source at the end.
What is the power of C? I mean,
it's just
equation C4. Is it C4?
Yeah, it is C4.
And then
When you do post-Newtonian analysis, it is important to keep track of powers of C. And then what you use is the fact that T00 is an energy density. But as we all know, E equal mc square, which means that in the energy density you have a C square.
yes, okay.
So this means C square over C4, finally, 1 over C square. But in T0I, in the angular momentum, you don't have C square, you have only C. In Tij, you don't have a power of C. So the components do not have the same scaling with C. But this is, here we do not do a post-Newtonian expansion. It's just a way of keeping track.
Okay. But here you have C square and C cube, and the expression
Yes,
of
yes.
this
Yeah,
boundary.
this is.
No, but the
You have.
first term is C square.
Yeah, don't worry. We will see power. Here we, yes.
I have a question on the notation IL minus 1.
Yes.
It's somehow ambiguous. I mean, the minus 1 subtracts
It
the
subtract.
sequence including I, or subtracts
No,
just,
no.
just L?
So capital L, each time there is a multi-index like capital L, by the way, you have to assume that it has its own name as index, I or J, or you can change the notation. It is a separate index. So L minus 1 means J1 to JL minus 1, and then you add an index I, just to, yes, indeed. Once you are used to it, it's very convenient because it's short to write it. Now, I want to describe this is linearized gravity. So it's just step number 0 or 1 at least. Now we want to do that for full Einstein's gravity nonlinear, okay? So it's just a tool to be able to solve explicitly Einstein equation, have integrals over the source, and then now we need to do something nonlinear. I will sketch which is this multipolar post-Minkowskian thing.
Is
And
there some notation for the epsilon IAV in the
epsilon Ig is the evidently Levi-Civita tensor in 3 dimensions. Yeah.
But is there some intuition why it comes there in the angular momentum?
Yeah, because the angular momentum. I did not write the formula, but the J itself, which is a tensor with L indices, like for instance, the L equal 1 will contain itself xib T0a xb. Okay, it will contain inside. This is the usual angular momentum density. This is the momentum density xb, so it is r cross p. Okay, integrated over the source. So it means there is an epsilon inside J, and there is an epsilon in front. It's the same epsilon. Okay. So the product of the two epsilon disappear. The formula does not depend on the orientation of space, but you need to decompose with respect to also the parity of space. Let me sketch, because evidently, as you can guess, things become complicated, richer, when you do the full Einstein's theory, nonlinear. But needed, okay? The point is that this linearized formula is just the building block, but now we need to solve Einstein equation nonlinearly, and nonlinear effects will be very important. So the logic is the following. I have a source, which may be, for instance, two black holes moving around, okay, or whatever system, and we want to compute the gravitational waves emitted by this system all over space. You know, both near the system, what is the action within the system of gravity from this to this, in the near zone of the system, and far away to see the wave coming out. It's very difficult to solve this problem if you try to do it in one go. That is to say, if you say, I will just write perturbation theory, post-Minkowskian, I write h mu nu as an integral of the source, and I iterate. In principle, you could do that, but quickly you cannot compute anything. It's too complicated. So the multipolar post-Minkowskian method was an idea of decomposing the problem in various parts. You surround the system by, you enclose it in a certain sphere in space and constant in time around the center of mass of the system, and you will decompose various regions of space-time. So there is the near zone of the system when you are at a distance which is distances much smaller than the wavelength emitted. The system has a characteristic period, so there is a characteristic wavelength, and first you want to solve the problem within a wavelength. Okay? In that case, you can use a post-Newtonian method to solve the field and the motion of the system near this. Okay? But now I want also to compute the emission, and for the emission of gravitational waves, I have to go to the wave zone. Okay? Actually, the way to do it is not to introduce immediately the wave zone, which would be larger than lambda, but to consider an exterior zone. So it is, let's say, it is something which is far away from the system, but which includes something of order lambda, and which extends over large distances at infinity in principle, except that actually you cannot go really to infinity because there are logarithmic problems in solving Einstein equation in the harmonic gauge. So you need three different things. You need really like the far wave zone, where you need, but this is like a detail, and this zone that we can call the exterior zone. So let me sketch what is done. So in the exterior zone, you want to solve Einstein's equation, but in vacuum now, because you don't see the source anymore. You solve Einstein equation in the vacuum, And you solve it by what is this multipolar post-Minkowskian method, which means what? You take G mu nu, you decompose it. Actually, you work with the Gothic metric. Okay? The Gothic metric is square root of G mu nu up. And this you can decompose as eta mu nu plus Gothic H mu nu up. Okay. And in harmonic gauge, this Gothic metric satisfies this equals 0. Okay, exactly now, because the harmonic gauge is that the d nu of this thing is exactly 0.
Don't insist as a square root of GB1? No.
No, certainly not. And by the way, G here is minus the determinant of the matrix, because I don't want to write square root of minus G all the time. Okay, you insert this in Einstein's equation. So essentially, you write this as, you know, eta mu nu plus something first order, H mu nu first order, plus G square second order. But now, how do you solve it? To first order, H mu nu will satisfy the same equation I was writing here with 0 in the right-hand side. So you can decompose H mu nu in terms of multiple moments. At this stage, you know the general solution of H mu nu outside first order is parametrized by two infinite set of multiple moments. You can always do that. I don't know yet how these multiple moments will be expressed in terms of the so. It's a way of parametrizing the metric. Then I insert that in Einstein equation to the second order, and what does it give me? It gives me like Laplace of now H to the second order. In the right-hand side will be complicated things that contain two derivatives and which is quadratic in H1. But I replace H1 as multiple expansions. So now in the right-hand side, you have something which is quadratic in this infinite set of multiples. It's a quadratic combination, which is explicit because I have two derivatives. I have special derivative acting on these multiple moments, you know, IL of t minus r over r, and another set L prime of t minus r over r, okay? So I can introduce infinite set of multiple moments to parameterize the solution, and now I need to solve this to second order. And
Why second order? Sorry, question.
but just you start, you know, you solve Einstein equation, we will go to fourth order, okay?
Oh, okay.
Yes, sure. But you start to second order.
Okay.
Yes, to start, okay? And, but now if you think of what is the right-hand side, you write it explicitly now because it is parameterized by function of t minus r over r with many derivatives, with products. So it means at each moment in the iteration, the right-hand side is a sum of terms which are of the type, you know, I mean, at each order, you can decompose them in, there will be powers of 1 over r, because here I have many powers of 1 over r. There will be function of t minus r, and there will be many n, many product of the unit vector. When you write explicitly things in t, r, and the unit vector. Okay?
Sorry, do you have some product of
Yes. Yes.
Product of y equals sum over y equivalent?
Yes, exactly. So in these things, the usual theorem which says that the tensor product of two irreducible representations is decomposed Clebsch-Gordan.
Yeah.
You do it, the Clebsch-Gordan thing, you do it, this is the interest of doing this with STF, because when you do it in the usual way, you say Clebsch-Gordan, oh my God, I will have square roots of things everywhere. How do I do that? Why here, let me give you an example. The basic idea is that if I take, for instance, two different vectors, a first vector and a second vector, you get a product of two vectors, okay? And you say, this was an irreducible representation of the rotation group. But now the product is not an irreducible representation. How do I decompose it in irreducible representation? Trivial. I just say this thing is a vector with two indices. I decompose it in it. So let me call this tensor Tij. And I decompose Tij in symmetric and anti-symmetric part. Okay, first step.
And then trace.
And then from this, I take away the trace. So this is the trace delta ij plus the part without trace. And this is antisymmetric, so I can write it as epsilon ija, the dual of this object here. So this decomposition of a general product of two vectors in a trace, a symmetric trace 3, and the epsilon ij of something which is a vector, because the dual is a vector, is exactly the usual group theory decomposition of L equal 1 times L equal 1, which goes from L equal 0, 1, and 2. This is 2. This is, it is 1 times 1 equal 0 plus 1 plus 2 as a group theory. But in Cartesian indices, you see always, you say, okay, let me take indices, project on symmetric trace 3. Actually, indeed, this is the crucial point where the Cartesian technology makes clearer what kind of symmetric trace 3 thing you will have, and also in calculations, because you don't need Clebsch-Gordan coefficients. You do the calculation with just tensor algebra. Okay, thank you for the question. Okay, yes, so what I wanted to say is now, but there are now technological points that I want to gloss over before stopping to go to the next thing, is when you multiply all those things, you have very high power of 1 over r in general. You have very high power of 1 over r because, for instance, a quadrupole is like 1 over r cubed at the origin. If I take the product of two quadrupoles, I have 1 over r to the 6. So I cannot, if I want to solve this equation, I would like to say H2 is the Laplace inverse, not Laplace again, D'Alembert operator, so the Green's function of the D'Alembert operator acting on this. But this is divergent at the origin at r equals 0. But evidently, this is a fictitious divergence because the origin is here. It's not in the exterior zone. So technologically, the way we did it was to use, again, analytic continuation. That is to say, you multiply the right-hand side by r divided by some scale to the power b, where b is a complex number. You can compute everything uniquely as a meromorphic function of b. And then you prove that if you take the finite part of this meromorphic extension of the right-hand side down to b equals 0, you have a solution of what you want, and you can slightly correct it to have a solution also of the gauge condition. So I just want to finish by saying that this way, because also we could have some integral formulae, like for instance, the reason why you can go is because you can, some of these complicated integrals you can compute. Actually, there are general formulas that you can derive when things are expressed in terms of t minus r with arbitrary function. You can write the solution as an explicit integral. So it means you have a tool to represent the solution to all order as well-defined meromorphically continued integrals of the multiple moments that you have put as seed multiple moments. And at the end of the thing, you need another step, which is, but these multiple moments that are just a way of parametrizing the general solution emitted by a source, I need to relate them to the source. And for this, you need the method of match asymptotic expansion that I had exposed for the motion of two black holes, expounded for the motion of two black holes. Here you need it to relate this exterior solution to the one you derive by post-Newtonian method. So all that is, I mean, in details, it is complicated. I mean, it took years to set up the thing, but at the end, it is an efficient method where you can compute to very high orders.
You said post-Newtonian.
Yes, because this is post-Newtonian, this is multipolar post-Minkowskian, and at some stage, you use both of them in order to relate what is outside with the source, okay? And the last point I will say is when you do that, you have one specific thing, which is that the source, the source emits like a linearized wave in the exterior domain. This linearized wave is non-linearly propagating with the other multipoles, including the monopole, which means that the mass of the source, which creates like an M over R field, which is included like the L equals 0 monopole, is also outside. And this M over R field is interacting, it's one of the nonlinear terms here at quadratic and cubic order, and then modifying the propagation of this field. So you have, let's say, diagrams, because if you want, you can write all this in terms of diagrams, where the propagation of gravity on the curved spacetime generated by the mass changes the propagation, and at the end, this is this term which gives the fact that a point in the spacetime here interacts with a point in spacetime here. They say the green function to go from here to here is not only the direct green function in flat spacetime, but also a green function, given by a diagram where it interacts. It's a loop diagram, and at the end, it means that there is an infinite non-locality in time, which enters at the fourth post-Newtonian approximation and which comes in the calculus. Okay, it was just to give a feeling. So at the end, there are explicit formulas that you can compute to high orders. Now they have been computed explicitly to 3.5 pn with some terms at 4 pn. Not yet to 4 pn because there are very delicate terms at 4 pn. My former PhD student Luc Blanchet is trying to crack this problem now. Okay. And the next thing, we will talk about effective one-body now after this.
When you say 4 pn, you mean c power 8?
Yes, 1 over c to the 8, v over c to the 8th power. The core of these lectures, which is to explain this effective one-body method, which will play the role to go to the link with scattering amplitudes. Okay? And to motivate it, let me remind you of the basic physics that we talk about. So we talk about a binary system, like of two black holes of two neutron stars, which for hundreds of millions of years have been going around very slowly around each other. For a very long time, they emit very little gravitational waves, so it means they get closer because they lose energy, but this is very slow, very adiabatic. So for a long time, you have what is called an inspiral, which means they go closer and closer, and in an adiabatic way. A result which had been obtained first by Peters in 1964 is if you consider in first approximation a Newtonian system which has energy and angular momentum, it is losing in the form of gravitational wave fluxes at infinity, both energy and angular momentum in the gravitational wave. But he found that the ratio of the loss of angular momentum to the loss of energy is such that the system tends to circularize before actually contracting a lot. It does, the size of the system contracts, but the eccentricity of the system, if it is of order 1 at the beginning, will go to 0 while the system is still far apart. So because of this, after a few 100 million years, the system can be considered like essentially zero eccentricity on circular orbit. And then this simplified our life enormously, because now you want to deal with very high perturbative order computation of things, but you have a system which goes on circular orbits, which simplifies the technology of computing things, multiple moments. There is only one period, which is the orbital period, and things like that.
Is that a classical or gravitational, or classical gravitation, or Einsteinian? Is that?
It's an Einsteinian gravitation, because we are talking about loss of energy and angular momentum. In Newtonian theory, you don't lose, you have no gravitational waves. So you need absolutely Einstein's thing. Now, how do you, in the period where you can use this adiabatic inspiral, I explained last time that what you can, an approximation to do things is to write that you have the energy of the system, and you write that the loss of energy in time, the loss of the energy of the system, you write it as minus the flux in the form of gravitational wave, energy flux at infinity, okay? But now we have a circular system. So in a circular system, you have two objects going around in circles, okay? Around, let's say, their center of mass. I'm not assuming they have equal mass, so the center of mass is not in the center between the two. And what is the orbital period? The orbital period is related to the mass and the distance by the two objects by Kepler's law. And let me remind you that Kepler's law can be recalled by using 1, 2, 3, which is 1 means you have GM, the sum of the masses. M is the sum of the masses. Okay, so I will always use the notation capital M for the sum of the masses. So Gm to the power 1 is omega square A cube, where omega is the circular frequency. Okay.
Third law, you mean?
Sorry?
That's the third law, you mean? Yes.
1, 2, 3 rule.
Third Kepler.
Yes, evidently. Okay. So the velocity would be omega A, and y, which would be omega 1 A1. Here you put 1, 2, 3, just to remember, because it's where is the 3? Okay, the 3 is on the A. So as a consequence, you can write that V, which is omega A, if you use this formula, can be written as Gm omega, and sorry, to the 1/3, so that you can define velocity as being Gm omega to the power 1/3 as a function of the circular frequency. If you divide by c cubed, this is a dimensionless, so it is V over c. If I take c equal 1, I call it sometimes just V, but V means V over c, okay? Just notation. So from the period, I compute a velocity. As the flux depends on the period, I can view it as a function of velocity. This I can view as a function of velocity. So this gives me a differential equation, dV by dt, you know, is equal to minus the flux as a function of V divided by the energy of the system differentiated with respect to V, okay? And when you use perturbation theory, you can compute the flux and the energies as power series in functions of V. This is what I explained. So perturbation theory is necessary and allows you to go quite near merger, okay? Near the end. But why it does not allow you to go near merger is, for instance, when you put number, you find that the flux of energy emitted as infinity as a function of this velocity parameter as an expression which is 32 over 5 nu square V to the 10 divided by something like G C to the 5, where nu, yes, the parameter nu will be very important in the following, so let me define it. Nu is the ratio of the effective mass divided by the total mass, where the effective mass is the product of the masses divided by the sum of the two masses. And mind you that M means the sum of the two masses. So
reduced mass?
So nu is the reduced mass in the sense of Newton, which is the equivalent mass in a two-body system for the relative motion. The ratio of effective mass to the total mass is a dimensionless parameter nu, which has a maximum value of 1/4 when they are equal mass, and which can be very small if one of the two masses is much smaller than the other one. Okay? This first term here, so there is an expansion which starts with this term. This is the Einstein quadrupole formula. And what I said quickly with slides in my first talk is that one has computed corrections to this that include V square, V cube, V4, up to V to the 7, okay? And it is necessary to have this accuracy. But now, if you look at the coefficient, I look just to be sure about the coefficient of the, let me write, the coefficient, they are log also, okay? 2V over C times V over C to the 6, okay? The term which is the 3pn correction. So this term is the 3pn correction, v to the c over 6. It has a complicated coefficient. If you put numbers in, this coefficient turns out to have a log and to have 123. And now we will see that the effective one-body method determines what is the frequency at merger, okay? So the system goes faster and faster. The orbital period diminishes. The orbital frequency increases. And then this means that this parameter v increases also. The value of this parameter v, or v over c, sorry, I'm changing my mind all the time whether v is dimensionless or not, is such that when you put number, v over c at merger, which is gm omega at merger, is something which is 0.19 to the 1/3, and this is 0.573. Okay. This means that v over c is slightly larger than 1/2 at merger. So it means the relative velocity formally is 57% of the velocity of light. So you see you are quite near the velocity of light, but still below. And when you put this number here, you find that this contribution is 4.37. So you have an expansion which is 1 plus, things order 1. I mean, the term that should be the smallest, 3pn, is larger than the first. So it shows clearly you cannot use these formulas at merger. Okay? Now, let me remind you, yes, of a basic thing about the Schwarzschild. Yes, let me go. Do I need this? Maybe I will explain it when I need it. So, in order to go beyond perturbation theory, in the late 1990s, we, with Alessandra Bonanno, have introduced a new method, the effective one-body method. As I told already, but let me repeat, that the original idea of this, not the idea as such, but the trigger that said, maybe there is something to look for, was one weekend where I was reading the Itzik on the Bear, just for fun. Rereading the book, Quantum Field Theory, in the French edition, because I've checked yesterday that in the English edition it's not written in the same way. In the French edition, which was a preprint of Saclay, of IPhT, that I had by accident, there was more detail about how to take into account mass ratio effects in the spectrum of hydrogen, taking the recoil of the proton, okay, in a relativistic way. And they were saying, you can resum Bethe, Salpeter, and so on. And they were giving references. And these references was with a work of Brezin, Itzikson, and Zin-Justin, in which they were resumming an infinite set of ladder and cross-ladder diagrams for two electromagnetically interacting particles, saying in some sense you can replace this two-body problem by something which looks like a one-body problem, although it was quite different. So the idea was there, okay? And then I thought, can we do that for gravity, okay? So first, just to clarify things, we are going now to discuss how the complicated Hamiltonian, which is behind this energy that I have written over some slides. You remember that the Hamiltonian between of interaction of two masses, point masses, but representing black holes, has been obtained up to the 4-loop level, which means V over C to the 8, as a perturbation expansion, which starts with Newton Hamiltonian, P square minus 1 over R, and then it has corrections V square over C square, V4 over C4, up to V8 over C8, okay? And this, you compute a two-body Hamiltonian, okay? When you do that, you have an Hamiltonian which depends on R1 minus R2, or X1 minus X2, the position in space of the two bodies, P1 and P2, okay? There is a first reduction of this two-body problem to a one-body problem, which is trivial, but except not so trivial actually, which is to say if I go to the center of mass, actually it's not so trivial, if I go to the center of mass, in the center of mass, even if I'm in a relativistic context, the definition of the center of mass is that P1 plus P2 equals 0, okay, even in a fully relativistic context and GR context, which means that P2 is not an independent variable from P1, and the common value of P1 and P2 I can call P. But what you find is that this P is canonically conjugate to X, which is X1 minus X2. And therefore, this Hamiltonian, if I replace P1 by P, P2 by minus P, and X1 minus X2 by X, or R, if you want, I have now an Hamiltonian which depends only on the relative motion. So I have already, in a sense, reduced the two-body problem to a one-body problem, but this is technically not useful yet, okay? What we will do is to reduce this problem by introducing a new idea. And the new idea is the following. Conceptually, yes, so the idea is how can I technically simplify the dynamics of a two-body system. Let me get rid of this also. I want to express the idea that this Hamiltonian, which is given by a complicated thing, will be equivalent to something much simpler, which it should be, in first approximation, a particle moving in an effective metric. So what you want to do is to replace the Hamiltonian for two-body systems, okay, M1 and M2 going around each other, for the Hamiltonian of a particle in space-time, in a fictitious space-time of mass mu, which satisfy the geodesic, in first approximation, action, in an effective metric, G mu nu effective, which is some metric that you construct, such that the geodesic motion of a particle of mass mu in this metric is equivalent to the two-body problem. This is the idea of mapping a complicated two-body problem in something much simpler conceptually. But now the first point is, how do you do that technically? What does it mean to say this is equivalent to this? And a nice way to think about it is to think that each problem is defined by energy levels, you know, energy levels as function of angular momentum. In quantum mechanics, the angular momentum is quantized in unit of h bar. L now means the angular momentum. By the way, L is, in multipoles, is the same L as before. It counts the representation, the dimension of representation of the rotation group for the states corresponding to this. And then I will have states, you know, like for the hydrogen atom, but now I have set of states for the real problem, which are parameterized by two integers, the integer L and the integer N, which is the radial quantum number, okay? For the real problem, but if I have a spherically symmetric effective metric, I will have also, the effective problem will have also energy levels. And you want to map this problem to this problem. And immediately it tells you how you should map things, because in quantum mechanics, as the levels are discrete, they are parameterized by integer, you want evidently each integer here to correspond to the same, this would be an effective integer here and the effective. You want this integer to be equal to this one and this to be equal to this one. Okay, what you don't know is here it is the effective, it is the energy of the effective particle, and here it is the energy of the real system. You don't know what is the value of this effective energy in terms of this effective energy. So you introduce an arbitrary function. Part of the problem is to find a function such that E real is a function of E effective. Is it in this form? Let us say, let's take it in this form. Okay. So you look for a function. So the problem is the following. You look for an effective metric, and you look for a function f such that you can map this and this. Yes?
May I ask a
Sure.
stupid question?
No questions are stupid.
How our problem of two rotating black holes is related to
Here I'm
quantum
assuming
mechanics?
yes, so there are two things. Yes. First, I can, good questions. I am, first, even if I have two masses which are, 30 times the mass of the sun, this is still a quantum mechanical system. I mean, we assume that quantum mechanics is universal, okay? Classical mechanics is just an approximation to quantum mechanics. What it means is that the levels are so thinly thing that I don't see the quantum structure, but I can always think that this is quantum mechanics, okay? Here it is just a conceptual aid. The way it aids is that it tells you I should identify this and this, but in the Bohr-Sommerfeld approximation, the value of the angular momentum and the quantum number n are what are called they are called the I integrals. They say the action integrals. Okay. When you solve a two-body problem, you have two action integrals, which is IR is 1/2 pi integral of PR dr, and I phi is 1/2 pi integral of P phi d phi. Okay. You have here I'm even taking, it's a three-dimensional problem, but it has spherical symmetry, so I can look in the plane, equatorial plane. I have the phi motion and the r motion. So I have the action integrals, and this spectrum classically means that the Hamiltonian is expressed as a function of the action integrals. You know that the two-body problem is formally integrable in the sense that perturbation theory keeps the integrability formally. I can express the Hamiltonian as a function of the action integrals by eliminating the angle, the angular variables. Okay? And therefore, this formula says that the real Hamiltonian as a function of the action integral has to be equal to a certain function of the effective Hamiltonian as a function of the same action integrals, because this part of the dictionary says that I must identify the action integrals. So now I have a technically well-defined things. If I want to find an effective metric, I have to compute the Hamiltonian for the real problem and for the effective problem as a function of the action integral. In France, this is called the Delaunay Hamiltonian, because Delaunay worked 20 years on this problem with big success for the motion of the moon. And how do you do it technically? Because immediately, there is the question, what do you do now? What are the calculations you do? How are you going to compute the effective metric? How are you going to compute all this stuff? Here, it was found technically very useful to come back to early quantum mechanics, because how did the first guy who computed this Hamiltonian to the relativistic effects did things? Sommerfeld. Sommerfeld used special techniques to compute these action integrals. And then we found, with Gerhard Schaefer, that it was very useful to go back to the book of Sommerfeld and find the techniques, because when you compute, how do you compute this? Let me sketch what you do. What you do is you write the Hamiltonian. So the Hamiltonian, which gives the value of the energy, is something like, it starts like p square, pr square. So it's p square minus 1/r, okay, when you scale everything. But p square is pr square plus angular momentum over r square minus 1/r, okay. At the Newtonian approximation, the Hamiltonian has a pr square, radial momentum square, the centrifugal potential L square over R square, the Newtonian potential minus 1/r, but it has then PR4, plus PR square over R square. There are many terms, evidently, beyond that, okay? You have a very complicated formula. But from this formula, you can compute PR as a function of the energy and as a function of L, okay? you solve an equation which is polynomial by perturbation theory because the PR is a small. So you just solve it, which means that this thing here, PR, is the square root. For instance, at the lowest approximation, it would be the square root of, it would be a factor 2, E plus 1 over R minus L square over R square, if I'm not mistaken, plus terms containing 1 over R square. So there will be R cube, 1 over R4, 1 over R5. You know, at the end, the radial momentum along the motion, expressed in terms of the energy, is a certain square root of something which contains 1 over R, 1 over R square, 1 over R cube, 1 over R4, 1 over R5.
And E and L.
Which depends on energy and angular momentum as parameters. Okay? So we are going to compute IR as a function of energy and angular momentum. Once we have computed that, it is enough to solve for E as a function of IR and L to get what we want. Okay? So this integral is the crucial integral to compute, which contains the answer. And now, how do you compute these integrals? Actually, these integrals are quite tricky because you need to compute between the roots, the lower root of this equation. This is, okay, this integral means what? I remind you that, yes, what we are talking about is an effective potential, which is something like that, which says that as a function of radius, when I fix the energy, the radius varies between a minimum value of the radius, which is when the two bodies are close to each other, and a maximum radius, periastron, apoastron. And in between, it goes like that, which means the body goes on an elliptic orbit. And this integral is the integral of PR dr over this excursion at fixed energy. Okay? To compute it, in principle, you need to compute what is this root, and then the square root, which is singular at the 2 points, and you want to compute that explicitly. Just to say that Sommerfeld understood that this integral, instead of writing it as a real integral, because along the r-axis, this thing is an integral along the r-axis between, so it is, let's say it is an integral on this axis. Yeah, let me use this axis here. Between this point and this point of a square root. So I want to compute this real integral. The main point of Sommerfeld method is to say a real integral, I can always go in the complex plane. And therefore, if I, instead of doing this integral, I deform the contour and do this, I will have twice the same integral because I go on both sides. But now I can move my contour arbitrarily in the complex plane, and I can expand in powers of small parameters because I do not depend on where were the roots and things like that. So using just contour integration, you can compute this without any effort. Okay? Otherwise, if you do it in a textbook way, it's much more complicated, especially to high perturbative order. So this is the way it was done. You compute then, you compute this quantity. Then now you want to compute the same thing for a different problem. The different problem is the following. We assume that the effective metric, ds square effective, can be written as minus a function of r dt square, c square dt square if I keep c, plus a function b over, I should clean up things, dr square, plus r square d omega square, the angle, d theta square plus sine square d theta. And then I write the mass shell condition for geodesic Hamilton-Jacobi equation. What is the Hamilton-Jacobi equation? It is the fact that the mass square plus g mu nu effective as a function of these coordinates, p mu equals 0. Okay?
And mu is not
mu. And this mu is not mu. Yes. Good. It is a test that people are following. This mu is this mu. So now I have something which contains again pr square plus p phi square and things like that. P phi is the same in the two problems. So this thing, I can also compute PR as a square root of things like that. And now, how do you do explicit computation? You do explicit computation by assuming that this function A and B have an expansion in powers of 1 over R of the following type. The function A, for instance, will be, in general, you should write it's 1 plus A1 over R plus A2 over R squared plus A3 over R cubed plus A4 over R4. So you parameterize a general metric that you don't know by saying it will have a post-Newtonian type expansion, 1 over R squared. Same thing for the B function. B of R is 1 plus B1 over R plus etc. Okay.
The original part is not changed.
And indeed, you keep this in the same way as in Schwarzschild coordinates. So if you use this in this thing, it gives again integrals of this type, so you can compute everything. So at the end, you can, so you have computed, maybe I've erased the crucial formula. The crucial formula was that the value of the real energy as a function of this integral IR and L for the real problem is related to the effective one by a function that I don't know yet. So I also need now to parameterize the arbitrary function. The way you parameterize the arbitrary function is in the following way. I will write it here before moving the thing up. You write E effective over mu c square, because it's convenient to work with dimensionless quantity. Mc square is an energy, so it's dimensionless, is a certain function of the real energy that I write as 1 plus the real energy minus, this is the binding energy. The binding energy means the real energy minus mc square. I subtract, it's just a convention, I subtract the rest mass contribution. So now, because it's closer to what I expect. And if you do things at the Newtonian level, that is to say, this problem has been solved by Newton in 1686 in the Newtonian approximation. So in this approximation, I know that I can identify the effective energy to just this term. Okay, so this term has a coefficient 1. But then at the next order, I can have something which is the real binding energy divided by mu c squared with an arbitrary coefficient alpha 1. And then at the next order, I can have something with a parameter alpha 2, and then this to the mu c square real binding square plus alpha 3, etc. So I identify, so at the end, you get a certain number of equations for a certain number of parameters. You know, at each order, you decompose things in powers of 1 over c squared. When c goes to infinity is the Newtonian limit. The first correction, 1 over c squared, is called the 1pn. 1 over c4 is called the... So at each order, you have algebraic equation to determine both the effective metric that you don't know yet and the map f between the two functions, which is parameterized by these parameters alpha 1, alpha 2. Yes, Ricardo?
I wanted to ask if there are no problems of gauge fixing for the effective...
Indeed, I mean there are no...
gauge fixing on the other side. How do you fix the gauge?
Yes, no, there is no problem in the sense you gauge fix it the way you want. And in particular here, it is important, I mean, it's not important conceptually, but technologically, you say, I go to a Schwarzschild gauge because when you fix the coefficient of the angular part, of the sphere part, in the effective metric to be r squared, this is called Schwarzschild type coordinates, so it fixes the gauge this way. But indeed, this gauge has nothing to do with what was the gauge, harmonic gauge, which was used, or ADM gauge, okay? But this difference will be absorbed in the map between the two, anyway. Yeah. Maybe I should indeed say it, because I did not say it. Both functions, you know, the energy, real or effective, has a function of IR and IJ and I phi. these are gauge invariant things. These functions are totally independent of the gauge I had chosen. And we have checked that explicitly, actually. So the physical gauge you use in space-time has disappeared anyway. And the effective gauge, you choose what you want for the calculation. Okay. So when you do things at the 0th approximation, which is the Newtonian approximation, you find that the only thing you need is that this coefficient A1. So at the Newtonian approximation, you just want A1 to be minus 2, which means minus 2 GM over C square. Okay. I did not put any factor here. Actually, you scale GM over C square somewhere just to keep things clean, and then you write minus 2. It's not, anyway, minus 2 GM over C square, if we want, for this full coefficient. So this is at the Newtonian approximation. So this was known to Newton. At the next order, what you find is that you have two equations for three unknowns. The three unknowns is A2, B1, and alpha 1. Because, so A2 is the next order in this metric. B1 is the first order in the function B. And alpha 1 is the first non-trivial coefficient that you don't know that relate the real energy to the effective energy that you allow for. But when you when you write this equation, you find that you have only two equations for three unknowns. Okay? Let me immediately mention that when you do it at 3pn, you have actually three equations for the three unknowns, which are the next level, which is A3, B2, and alpha 2. Okay? And at 3pn, actually, you have four equations for three unknowns, which is A4, B3, and alpha 3. Okay? Now, if you make the sum of equations here and the sum of unknowns here, you have 9 and 9. So you could think, if I wait until the 3pn level, I will have as many equations as unknowns. But this is not what we did, because anyway, we had only the 2pn thing. And also, when you do that, the solution is very complicated, looks bad. It's not what you want. Okay? So the good solution is the following. You assume something, which is this value of A1, you see, is the first coefficient in the metric. And this value means that the function A starts like 1 minus 2 GM over C square R, which is the Schwarzschild metric. Okay. So this is saying, to lowest approximation, I have the Schwarzschild metric in the A component. And it is very natural to say, let's assume that plus terms of 1 over C4, okay? Next correction. Let's assume that in the B function, I have also the Schwarzschild metric, so that it starts like that, plus correction, something beyond this, which means let's assume that B1 is plus 2 GM over C squared. So at this stage, let's add a constraint that this B1 is determined this way. Then it gives you two equations for two unknowns. At the next level, you have three equations for three unknowns. So you have a unique solution up to the 3pn level. And what is nice is that this solution is very simple. Okay? It's very simple in the sense that at 2pn, let me write this. Yes. Okay, let me, what do I want to say here so that I have already explained. Yes. Let me state the first statement. Yeah. The first statement is that if you remember from the slides of my first talk, where I had written what was the Hamiltonian at the first post-Newtonian approximation as determined by Einstein in Ferlofman in 1938. Okay? This was a complicated Hamiltonian which had already 7 coefficients, okay, with 3.5, 7.5, things like that. Now, when you solve this, when you solve these two equations plus this assumption for the two unknowns, you find that the result is that A2 is equal to 0 and alpha 1 equal nu over 2. Okay. What it means is that at the 1pn approximation, this transformation has only this coefficient non-zero, but when you write explicitly what it means that the effective energy is the same as this effective energy. Okay. Mu c square is equal to the square of the real energy minus m1 square c4 minus m2 square c4 divided by 2 m1 m2 c4. That is to say, what we are going to find is that at all post-Newtonian orders, we will find that the relation between the effective energy and the real energy is given by the same formula. It will never be corrected. And I have shown recently that this is true to all orders. That is to say, that in this framework, you must say that the relation between the real energy and the effective energy is this, which means that the effective energy is, the Mandelstam S parameter, squared energy thing. This formula actually was in the paper of Brezin, Itzikson, Zin, Justin, but we did not assume, because this formula is finally very natural. When you think about relation of a two-body problem and one-body problem, by some reasoning, this is the most natural formula you write. But here it is not assumed. It is a consequence that is a necessary consequence. So this is a basic tool in effective one-body. The real energy is related to the effective energy by this formula. Okay. Once this is true, let's look at the metric. The fact that A2 equals 0, okay, means that at 1pn, you have the following result. If I take an effective metric, which is, let me define also among my notation here, let me define gm over c square r, which is a dimensional thing, as u. Yes, u is a notation for gm over c square r because you write g square over c square r all the time, so you don't want to write it all the time.
But you already use u as a...
Small u. Yes?
It's big u.
It's a small u here.
No, you already use it, but...
T minus r over c was also.
That's true. Sorry.
Here,
That's true. That's true.
They differ by the same notation.
Yes, exactly. Indeed. So this means that I have an effective metric, which is minus 1 over u plus dr square over 1 minus 2u plus r square d theta square plus sine square theta d phi square. But this metric is the Schwarzschild metric. So the conclusion is that if you take a test this is the very nice thing. If you test a test particle of mass mu moving geodesically in an effective Schwarzschild metric, but then you take the energy you transform in the real energy by hey.
A bit more. You can push the.
I can push it
first
up.
one.
And I should have done in reverse. No, it works.
You can force.
It worked. I can erase this. So the conclusion is that a test particle moving in Schwarzschild with just this transformation of energy is equivalent to the complicated Hamiltonian of Einstein in Verloffmann. So instead of having 7 complicated coefficients, I have no information at all. The only thing is this transformation. Okay, first result at the 1pn level. Now, at the 2pn level, yes, now I have a problem at the 2pn level. Maybe I can do the reverse. At the 2pn level, but I need to be down. At the 2pn level, what you find is that this function, so let me say that this function is called A of u.
1pn means v square over c square.
Yes, after Newton, okay? And let me introduce, here there is the function b of u, dr square. And let me introduce also the function, the product AB, because in Schwarzschild the product AB is 1, okay? So you introduce AB, you say this is a function d of u, and sometimes you say this is the inverse of a function that you call d bar of u. So you can parameterize a general metric by A of u and d bar of u. what you find is that A of u, yeah, I should say that at the 1pn level, there could be a correction here of order u square, but the fact that this coefficient is 0 means I don't have a correction, you see? I don't have a nonlinear correction. The first correction is at u cube, and which is 2pn, and at just a coefficient 2 nu. And then the function d bar of u at 2pn is also very simple. It is 1 plus 6 nu u square. So when you do things at 2pn, which means you have 11 coefficients in the Hamiltonian, I mean, it's a complicated, really complicated Hamiltonian. These 11 coefficients are equivalent to saying I have a coefficient 2 here, and I have a coefficient 6 here, and I have this, this transformation between energy, which is not modified, because you find that at each order, alpha 2 equals 0, alpha 3 equals 0, alpha 4 equals 0. By calculations, there could be non-zero.
It is valid to any order now?
Yes, then I have shown it is valid to any order, that this formula is exact. Okay? So it shows the simplicity. You know, from 11 parameters, you go to only 2 parameters. Why, by the way? Why? Simply because most of these 11 parameters were gauge effects, and because here you work with gauge invariant things using canonical transformations, because the fact that you identified action variables between two Hamiltonian means you have done a canonical transformation in phase space. And canonical transformations are much richer than gauge transformation in space-time, actually. They contain, you know, a function of 2 variables, f of qp, the generating function. At the next order, what you find, where the next order, you have really, you know, you have something with more than 20 coefficients in the Hamiltonian, quite complicated. Again, everything will be condensed actually in 3 coefficients, okay? At the next order, you find that you must add a term here, which is 94 over 3 minus 41 over 32 pi square. So it becomes irrational at this order, and transcendental even, u4. Okay, and here there is a coefficient which is plus 52 minus 6 nu times nu u cube. Okay, but you, as I said, as we had imposed this condition, at the next order you have actually more equations than unknowns, and in order to solve the problem, you need a little flexibility more. And this little flexibility, we realize, is very natural. As anyway, we are representing, you know, a complicated 2-body problem by a much simpler 1-body problem. But this 1-body problem, you don't need to say it is exactly geodesic. It could have corrections here, which are like q, nu nu, rho, sigma, p mu, p nu, p rho, p sigma. Corrections to the mass shell condition, which are quartic in momenta and not only quadratic. So it's a Finsler type of correction of the geodesic motion, okay? Slight complication. But when you do that, you find now it adds a lot of flexibility, so much that it is very easy to solve the problem, and you can actually arrange things so that this term, you must have this term, but this term is just, so it means this term this term is equivalent to modifying mu square, you know, by an extra factor, okay? So it modifies mu square by mu square equal 1 plus 2, 4 minus 3 nu, nu u square, pr over mu 4. So you have a term quartic in momenta, but with a very simple coefficients, okay? And then you can continue formally to all orders. We did that at the 4pn order, which is the last order which is known fully. And at the 4pn order, what happens is that there is, as I said quickly, there is a non-local term in the Hamiltonian. And this non-local term actually can be absorbed with an infinite series in PR, okay? Otherwise, you leave it as a non-local term. Now, the main point that I want to finish with is to explain why this thing was useful to go to the merger, okay? And what we did to do that. So, when I have an effective problem, let me discuss, yes. First, I should say that we found technically convenient, but I will have to come back to this issue, to put as many corrections as possible in the radial momentum square. The reason is, as I said before, the binary system goes on a circular orbit. If you use a gauge where some of the dynamics is in PR, as PR is 0 to lowest order, if you put it PR4, it has a negligible effect in most of the discussion. So this way, you don't even need to use these terms, okay? So this is what we did. And in particular, if you look at the, if I write that the effective energy square divided by mu square, I write this condition, okay. This condition has P0 square with the inverse of A. So this thing means energy square divided by A with a minus sign. The PR square gives PR square divided by B. And then this term gives P phi square, the angular momentum, divided by R square, the centrifugal potential. If I solve this equation, what I find is that E square over mu is A of R times, when I divide things, 1 plus L square over R square, okay, plus PR square over B, okay, of U.
I'm sorry, divided by mu or mu C square?
Yes, now I was ready to make you believe that C becomes 1 at some level, to simplify, okay? Also here I have to see the units I use. But let's now scale things to get the essence of the thing. This is a relation, this is the Hamiltonian as a function of P phi square and R square, okay? So it contains the centrifugal potential, L square over R square. It contains, if I look at circular orbit, I can neglect this. And then along circular orbits, this defines an effective potential which gives energy or energy square, let's call this E hat, square as a function of R, okay? And for Schwarzschild, for instance, this function is 1 minus 2 gm over R, okay? And therefore, this function vanishes at R equal 2 gm, while this function is 1 plus. So at the end, you find that this thing has this shape, okay? At infinity, this goes to 1. Okay. In relativistic, in the physics of a particle going around a black hole, a central feature of the physics of how a particle goes around a black hole is that its effective potential is the product, not the sum. In Newtonian physics, the effective potential would be, 1 minus 1 over R plus L square over 2R square. It would be the sum. And then this thing is the centrifugal barrier, which in Newtonian physics would go like L square over R square, okay, up to infinity. And then in Newtonian physics, you have circular orbits which are as close as you want because the centrifugal barrier is infinitely high. When you have a black hole, the centrifugal barrier is multiplied by 1 minus 2 m over r, which means it goes down to 0. And this is the central property of the particle around the black hole, which means the following. If I have a particle going around the black hole, which is losing energy and angular momentum at infinity, what happens is that the particle goes around, at fixed energy along in general, non-circular orbit, elliptic orbit.
But outside of the horizon.
Outside of the horizon for the moment. As I said before, this particle loses eccentricity, which means that it goes down to the bottom of this thing, because this bottom means you have no eccentricity. Otherwise, you go from R min to R max, okay? So a particle going in circular orbit around a black hole is located here. Let's assume this particle is losing angular momentum, okay, and energy. What happens is the height of this barrier is defined by the centrifugal term. So what happens is that this barrier goes down because the angular momentum goes down, goes down. So what happens is that slowly the particle, moves here and then moves here and then moves here. But at some point, the centrifugal barrier goes to 0. This effective potential has a saddle, as a, how is it called? The triple point. Inflection point. Yeah, as an inflection point, which means that there is a last orbit where you can go around in a stable manner. And this thing for a Schwarzschild black hole is 6 GM, 3 times the Schwarzschild radius. So for a test particle around a Schwarzschild black hole, if you are at 3 times the horizon, this is the last stable circular orbit. If you are below this thing, you have a potential which is now, like that, which means you plunge. You have nothing, you have no centrifugal barrier anymore. So what this means is a test particle around a black hole will go around a circular orbit in spiral up to the moment where it reaches 6 GM. And after that, nothing will prevent the particle from going to the horizon. This is for a test particle in a Schwarzschild background. But the fact that the EOB method has been transcribing the complicated Hamiltonian in a form which is of this type. The only difference is that the A function has been changed. The A function is no longer, 1 minus 2u, but it is 1 minus 2u plus 2 nu u cubed plus this. So the basic idea of EOB was to say, let us trust now that this is a good representation of the A function, and let us see if it qualitatively predicts the same thing. And what happened is that when we first computed that with Alessandra at the 2pn level, this function here, so now let me plot this function A as, because this is, you see, what is crucial here was that this function at the 0, so this function A as a function of R, for Schwarzschild, this function is 1 minus 2 over R when I scale GM to 1, okay? So it was a function which goes to 1 for large R and which has a 0.
Which describes the horizon.
Which describes the horizon, exactly. So the 0 of this function corresponds to the horizon. But we will never finally go to the horizon because there is the plunge before that. Okay, we will see what happens. Now, if you take this function, which is the next correction, you find that it is a little bit above, but it still has a 0. So qualitatively, it predicts exactly the same type of things, that there is a last stable orbit, then there is a plunge and things like that. Now, we had a surprise in 2001 when with Gerhard Schaefer and Piotr Aronofsky, we computed the next term, which is uniquely fixed, because this coefficient is large. 94 over 3 is large, in spite of the pi square. And then what you find is if you plot this function as it is like that, but then it misses 0 and goes up. At this stage, we said, let's not worry. We replace, it's a Taylor expansion. It's an expansion in powers of u. We all know that Taylor expansions become bad when you go too far. Let's replace it by a Padé approximant. I remember at the time I called Jean Justin, to say, what are the, do you have a better resummation method than Padé? And then he told me, no, if you don't know something very precise, Padé is a good choice, okay? So what you do is you say, let's replace this function by its Padé of the type 1 and n down. Why 1 up? 1 up means you write Padé as 1 plus linear in u divided by 1 plus something u plus u square plus u cube, okay? But because you put 1 plus u down, you, in a sense, you suggest to this function to have a 0 like 1 minus 2u, okay? So that's what you do anyway. You assume this, and then this Padé becomes like that, and then qualitatively predicts something completely similar, and the same is true at 4pn when you use a Padé. And this way you can predict what is the orbital frequency at the last stable orbit, but you can also predict what happens during the plunge, because when you use this and evolve the two-body problem in this effective one-body, you find that you have a potential which becomes like that. You find that after crossing, the last stable orbit is no longer at 6 GM. It is a little bit closer with higher frequency. So everything is, quantitatively changed, which means that it's higher frequency that you reach, because if you get closer, you go faster. So you can predict what is the frequency of the two bodies at the moment where they will suddenly feel that they cannot go on a circular orbit anymore. When you compute what happens during the plunge, you find that this quantity, which is like the radial momentum, that before that people assume that after the plunge you really plunge radially. No, it's not correct. Actually, you plunge going around, and essentially you still have a very small radial kinetic energy of radial motion. Most of the energy is in L square over R square. And then at the end, what you compute, let me finish saying this, and anyway, I am at the end of this, is when you compute so you have an Hamiltonian problem. You write on the Hamiltonian problem a radiation reaction force, which is a resum version of what I exposed in the first hour. In the first hour, I exposed the way to compute the flux to all orders in V over C. I said it's not well convergent, so you replace it by resumming it in a different way. Then it gives you a radiation reaction force that you can write even during the plunge, okay? And when you do that, at the end, you find that the orbital frequency omega as a function of time is something which increases in time, but which has a maximum at some moment during the plunge, before reaching the horizon. Okay, the horizon would be like going to this point. So during the plunge,
Energy graph.
this is omega. This is the orbital frequency, which is what you see at infinity, because the orbital frequency emits gravitational waves proportional to this. It's the same frequency in the gravitational waves. And you find also that the amplitude of the gravitational waves that you emit, as it is in good approximation a function of omega, the amplitude of the gravitational waves also will have a maximum at a certain point in time that you can compute in the method. And now what we did was to say, let's define merger as the moment of maximum amplitude of this thing and maximum frequency. And after this point, we stop using the effective one-body description, and we say this is the merger of the two black holes, and the gravitational waves that I have computed at this moment, I match it to a sum of vibration modes of the form black hole with the energy and angular momentum computed at this moment, so it's fully predictive. And when you do that, this is the way, with Alessandra, we first computed, the complete gravitational waves that I had shown on my slide, which was the gravitational waves emitted during early in spiral, late in spiral, the plunge, the merger, and the post-merger, okay? So this was like an approximate method saying, okay, we do the best, we resum, we have a description which seems to be able to go something which looks like merger. Let's be bold and say it will predict to some approximation the gravitational waves. And this thing has been shown to be in rather good agreement when the full numerical relativity simulation of two black holes came on the market later. Okay, that ends today's lecture.
So the plunge begins at 3 Schwarzschild rings.
Yes, in the Schwarzschild case.
So it's like
And the merger is also, and the peak is the plunge, or I didn't catch the last?
So the peak is during the plunge. After,
After the
yes,
interval.
the plunge is here, yes. So there is, yes, no, this is important. The last stable orbit is somewhere there.
Okay.
You don't, I mean, what happened historically is in our paper we said, okay, let's go to the last stable orbit because everything is under control. But then when we computed beyond the last stable orbit, we said nothing prevents us to be more predictive. And the only limit of predictability was this because it looked, I knew also that in the case of test particle black hole, something happened in this case, so it was the natural choice. But this is like, actually, this point, I should say, is like 3m, which is now 3/2 the Schwarzschild radius, which is the so-called light ring. Light ring is around the black hole, is a radius where light, which means something, massless particle, can go around, okay? But it is not defined like that in the formalism. It's defined really as the maximum of omega, but it happens for some reason to be the light. And for some reasons, I knew that the light ring is really the reason which the radius where it corresponds to merger in the sense of screening quasi-normal mode emission.